Yeah, I'm happy to introduce Jaye Verniero here up to us. Jaye got their bachelor's at American University of DC and a PhD in applied math, University of Iowa. Went on to postdoc at Berkeley to look at and study solar probe data, and is now at Goddard doing that and many other things. And you're going to talk to us today about trans-disciplinary approach for tracing the energy flow throughout the heliosphere.
All right, great. Thanks so much for the introduction. Hopefully everyone can hear me okay online if there's anyone there. But yeah, thanks so much for coming. I'm Jaye Verniero. I use they, he pronouns in a fluid sense, just like my research interests, which you will see today. So I'm in the Heliophysics division at Goddard. And what is heliophysics? It was born out of many disciplines, solar physics, plasma physics, trying to understand the sun and how the sun influences its surroundings. So you can think of it as, we got these silos. You can think of that as, let's say you had a plate of fruit randomly placed, the apples are over here, the bananas over here, not really touching each other. And multi-disciplinary is kind of like a fruit platter where somebody intentionally laid the melon on top of the pineapple. And then interdisciplinary, kind of like that fruit salad. That's an intentionally made delicious snack. But I am searching for that higher level synthesis, the trans-disciplinary fruit smoothie. Something that is greater than the sum of its parts. And there's so many outstanding questions in the universe, it might take some creativity to understand it. So the other day, I was sitting around and thinking about the heliosphere, and I thought to myself, why don't these disparate parts really talk to each other? We're all segregated into these different portions of the heliosphere. We got the solar folks. We study things ejected from the sun, CMEs, flares. We can recategorize those as explosive energetic events. And we got the inner helio people who study the open field lines, the space between solar wind and turbulence. Those are energy transport pathways. Then we have, planetary folks. Earth is a planet. ITM, Reconnection, Aurora physics. And those are all energy coupling within the heliosphere. And then, of course, we got the outer helio folks, like galactic cosmic rays. What's the shape of the heliosphere? And that's energy coupling between the heliosphere and the interstellar medium. And then you can also ask, what's a black hole's sphere of influence on the heliosphere? Does it? Good, maybe. I know at Goddard, every portion of groups is actually a different funding division, and astrophysics is a completely different building you have to drive to. So I wonder what would happen if we were all in the same building and not under those labels. But what I do know is we all have some common things about us that are true in virtually every boundary region of the heliosphere. That's turbulence, with particle interactions, instabilities, the evolution of particle velocity distribution functions, or VDFs, and much more. I'm going to touch upon almost all of these topics today, only slightly, to give you a flavor of what I'm interested in. So first, I'm going to start with turbulence. The word turbulence, or la turbulenza, was first coined by Leonardo da Vinci in the year 1500, when they drew this beautiful drawing of turbulent water flow. And it's in they have this book called Codex Atlanticus, and it has the first drawings of flight, the first drawings of the water wheel. And Leonardo was a real transdisciplinarian, more than just an artist, but a great scientist. And in this drawing, you can see there's this hidden Da Vinci code, and they asked 3 questions about turbulence that are actually still relevant today. Where is turbulence in water generated? Where does turbulence in water persist for long times? And where does turbulence in water come to rest? So just to give you appreciation for how amazing this was. So Leonardo drew the water in 1500, and that was 137 years before Rene Descartes said, "I think, therefore I have a coordinate system." Before then, we couldn't even graph functions. So how on earth can any scientist even visualize anything? All we had was artists at that time. And then a couple of years later, Leibniz invented calculus. Oh, sorry, I'm a physicist. Newton invented calculus. And then once we had a way to try to understand how things change with time, Navier-Stokes came along and wrote their famous equations describing the motion of a viscous fluid. And then only about 50 years later, Reynolds came along and wrote down his famous Reynolds number, try to classify turbulent flow. Let's take a look at that beautiful equation. So let's say we have an incompressible viscous fluid with some flow velocity u, and we start with our trusty F equals ma. Well, the sum of the forces on this left-hand side is the pressure term plus this linear viscous term. Our m is the linear mass density, and our acceleration term is the sum of this instantaneous time evolution of a flow plus this nonlinear term. And so Reynolds came along and he said, "Hey, what if I just took the ratio of the nonlinear term to the linear term? That's on length scale L. And what if that ratio was greater than 100? Well, that would mean that the nonlinear term dominates, and so we have turbulence. But existence and smoothness of this equation does not hold in 3D, or does it? This is one of the famous millennial problems. So if you don't know what a millennial problem is, it's a list of math problems. You can Google it right now, about 10 of them, that if you solve one of them, it will greatly benefit society. And you can win $1 million if you prove any one of them or disprove. And so I'm still waiting for my million. I think hopefully it will come soon. So beginning about waves on a string, waves on a string work the same way in space. So let's say you have some guitar string, for example, and the guitar string has some tension T and some linear mass density. Well, then the velocity, if you pluck it, is just square root of T over that linear mass density. And you also have these beautiful resonances, as some integer multiple of the frequency. The same thing happens. I don't know if anyone here plays guitar or a stringed instrument, but if you actually, let's say this is length L, if you pluck the string at L over 2, you can actually get these beautiful harmonics. And the same is true in space. Let's say we have an affine wave, and the string in this case is the magnetic field line. And instead of tension, we have magnetic field. So it's really just the exact same process. Not exact, but. So affine waves are really interesting. So this is this equation right here is the same exact form as Navier-Stokes as we saw before. And we can think of affine waves as these, we think of turbulence as affine waves actually colliding together. And that is actually what leads to the nonlinear term dominating over the linear term, is when these affine waves actually collide. And this way, affine wave collisions are considered the fundamental building block of plasma turbulence. And so because of this, for part of my thesis work a while ago, I made a visualization of these three-dimensional perpendicularly polarized affine waves colliding. So I have these initial conditions, and let's see, here are streamlines. So this represents the magnetic field, and these contours. So these contours right here are just the current in the z direction. But first, it's a very simple mode. And also this was this visualization was done with a gyrokinetic turbulence simulation. And so let this go. They're going to collide, and now all of these, we got more wiggles afterwards, and so that means that higher wave numbers were cascaded to smaller scales, and then it's going to collide at the boundary again, and you can see it's getting a lot more wiggles. And so much more modes were excited, and it comes back together. So that is one way to visualize turbulence, slightly different than the drawing of water. So, and then we have Richardson in 1920 wrote a book. He was a weatherman, actually, talking about clouds. He said, big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on, to viscosity. So what does that mean? How many people drink coffee in this room? Great, that was a trick question. So, you know, anyone ever wonder why it only takes one stir to pour cream into coffee, and then the coffee and then actually just mixes together? So that's because coffee is a turbulent medium. And so let's say you have your initial stir at some length scale L. Well, that one stir is your injection of energy, and then that one stir turns to two smaller stirs, and then four smaller stirs, and so on to viscosity, and eventually converted to heat. Then Kolmogorov came around in 1941. Fun fact, Kolmogorov was a mathematician. He actually mentioned nothing about physics in his original papers about this, which I think is fun. But he was able to, have this picture in our minds where here's the log scale of kinetic energy versus wave number. So this is an exact description of what I just said, where you have some energy injected at some driving scale L. And then once that energy cascades to smaller length scales at a constant rate, and this is called the inertial range. And then eventually, once it gets to some viscous scale, it's going to damp out and it gets dissipated. So same thing is true in space, where in space physics, the big question of turbulence is how do we understand the entire dynamics of from large scale motions and all the way down, how is it dissipated to plasma heat? And so this is the turbulence. This is the spectrum that's actually measured in observations, and the crux of the puzzle is right here in this transition region. When the energy is done cascading and it finally gets to the length scale of an ion. So this is where this frequency range is. Once that stir is actually small enough at the same spatial scale as the proton general radius, then it can finally talk to each other, and that's when it exchanges energy. Then the ion can do what it wants with it. So there's been a lot of proposed mechanisms for how exactly this happens. I don't think it's just one thing. It's probably a combination of all these things, but some of them include magnetic reconnection, with particle interactions, shocks, you name it. So I'm sure many of you have seen this picture before, solar wind. One of the outstanding questions I'm sure you all know is the coronal heating problem. Why is the sun so hot? We don't know that basic question, among many other things, but luckily we have Parker Solar Probe that is trying to find out. So Parker Solar Probe is supporting this ongoing mystery: who, what, when, where, why, and how does cosmic energy flow? If you think about sun, it's so big. How does it talk to something as small as an electron? I mean, the time scales and the length scales just don't make sense. Is there a special telephone line? What happens? So I'm attacking this problem from the perspective of the proton beam. So this is a representation of a velocity distribution function. So we measure the particles as a function of energy, and we count how many particles come in at a certain energy, and we create this distribution of energy. So the universe loves to be in balance. It loves equilibrium, and the most happiest state the universe can be in is in a totally random state, which would be represented by just a Maxwellian, so just this portion. And then sometimes we get this other portion out here called the beam, this other population that deviates from that symmetry, and it gets a little existential. we constantly wonder where the beam comes from. What we do know is that once there is this extra asymmetry, because the VDF will do anything it can to go back to symmetry, the beam portion will move around in phase space to get back to the equilibrium. And in that process, it will emit energy, and oftentimes in the form of waves. So what I do on Parker Solar Probe right now is I look at both the waves instrument, the fields instrument, and the particle instrument suite, and try to understand how waves and particles exchange energy. So Helios first saw the proton beam in 1982, Eckert Marsch. And traditionally, when folks try to characterize the distribution function, they use a sum of bi-Maxwellians to fit the distribution. One Maxwellian for the core part, for that symmetric part, and one for the beam part. And then from fitting those parameters, you can get things like density and temperature. For example, the temperature would be the width of these things. So the shape of this data can really tell you about physical parameters. So then I wanted to see what the beams look like. 36 solar radii. So this was Encounter 2. This wave event right here is really what started my interest in this for, I guess, the next 4 years. Oof. So where I'm going to put it so I can show what the panels are. So these top panels up here are the proton velocity distribution functions, just in different ways of looking at it. So this portion right here is a three-dimensional version where every line is a different cut in angle. And these two are two-dimensional contours. This arrow right here is the magnetic field direction, so you can see what's perpendicular and what's parallel. And the length of the arrow is the Alpine speed. This panel over here, it looks like the distribution is cut off. That's because it is. It's actually blocked off by the heat shield. And then these two panels here represents the wavelet transform of the electromagnetic field data. And so you can see during this event, there is a very narrow coherent frequency band at the same time as this very narrow left-handed polarization. So left-handed as in it's blue in the spacecraft frame. And this white line here is right at the proton gyro frequency. So right at the proton gyro frequency, we get these very darkly coherent waves. And this panel right here is actually the exact same thing as these three, just in a different way. It's the energy of the protons. And so we're going to see what happens. So here's the time here. So at first, there's power at all scales, nothing much happening, no beam. And then VDFs are mostly isotropic. And then we get to this beam part, and you can see how this tail is growing and growing the same time as these waves. This higher energy tail is going to grow so much, it's going to actually almost overtake the main part of it. Now, this is a period that's almost 2 hours long, which is quite, at this time in the mission was quite significant, comparing to Helios and other spacecraft. But yeah, you can see now it's really ramping up, and it's not just one giant distribution at this point. This is this spectacular wave event, and still don't know where that beam originally came from, but hopefully in the next few years I'll figure it out. Anyone have any questions so far?
Quick question, actually. Yeah, is the beam at all related to the straw population sense, or is that maybe it's assumed an extra?
Oh.
It's parallel.
Oh, do you mean straw as an electron straw?
Yeah, I guess these are ions, right?
Yeah, so these
Okay.
are ions, but beam and straw, straw is German for beam. So
Okay.
I would say it's analogous.
Yeah, okay.
I'll get to the straw later.
Okay.
Good question. Okay, so first with this wave event, I was able to fit the distribution to a sum of bi-Maxwellians in a reduced parameter space, because at that time we can only do 1D fits. I'm not sure of this now, but at that time I threw the fits in a plasma instability solver called Plumage, and was able to show that the beam was actually responsible for these positive wave growths. Then we got into 22 Solar Radii, Encounter 4, and things looked a lot different. Instead of this nicely coherent left-handed polarization signature, the red here means right-handed. So all of a sudden, the waves had a different polarization. And also we were in very, very slow wind. The wind got, this is the first time we saw the very slow wind at 200 kilometers per second. And really started to wonder, why does the beam look like this? So you could, this is in V parallel V perp space. And the beam started to diffuse perpendicularly. And thanks to some of our friends in the room, we were able to show that using quasi-linear theory, that there was indeed a specific resonance that was going on with these waves that would correlate with these quasi-linear diffusion contours. And it just so happens that they luckily lined up with this beam. So if anyone wants to read more about it, just go here. So just to connect it back to the spectrum of turbulence, this right here is exactly where those waves were, right at the proton scale. Good. So PSP is showing us these exotic VDFs, and it really does require us to think of new ways of characterizing the symmetries and the asymmetries that are leading to energy transfer and subsequent plasma heating. So what do I mean by symmetry? I mean, the core part, the symmetric part, the happy part, and then the asymmetric part is like a beam. So in order to try to characterize that strange looking VDF I showed, I tried to use triple bimaximum fitting. Just fit a third Gaussian to this thing to see if it captured anything. But it still wasn't satisfying, it still wasn't enough. And then I helped out with a project that tried to use Hermite polynomials in order to characterize this. So, if you're doing a Gaussian fitting to something, a Gaussian is actually just a basis that you want to organize your data in a certain way, and that basis is gonna tell you something.
So if I understand well, like if you have the plot on the left, which is like the 2D view, just on the right, you have like these, that would be kind of 1D cut for one angle, right?
Yes.
And when you do the Maxwellian fits, that's in 1D, right?
Oh, no, no, it's not 1D, it's actually 3D.
Yeah, 3D because you have but all what I'm saying, like, do you, like, when you do like the Maxwellian fit, you only do that on like the 1D data?
Oh, no, I do it on the 3D. I have like, I'm just showing like 2 or 4 grid spaces, but I have like a full every slice.
Okay.
Yeah. But yeah, so just like how the Gaussians are a basis for this scenario, Hermite polynomials are also just a different kind of basis to try to characterize. But then I think about even further than that. If you think about these particles come in, they use what's called an electrostatic analyzer, and basically particles come into the detector, and what comes down to the ground is this matrix of counts, and then these matrix of counts is organized with energy and phase space. And these counts are coming from physics. And so in theory, there should be some pattern you could extract from this matrix itself. So then you can start to play around with things like singular value decomposition. What if you just took the matrix and did a singular value decomposition and then use that as your basis? That is a data-driven basis that doesn't require your choice of polynomials or what have you. And so that's what I tried to do with that same period of time. I can did the singular value decomposition, and then I computed the entropy, and I was able to pick out that perpendicular diffusive part that's having the place with highest entropy. And so I started to ask myself, what does this mean? Does higher entropy, does that mean loss of information, loss of symmetry? These are open questions that just dive into information theory that I won't get into, but this project is definitely a work in progress. But if anybody has any ideas, well, please talk to me afterwards. So what's going on here? So VDFs that break symmetry are carrying information about where the energy is going. where does turbulence come to rest? Where does the energy go? The same question is, where does the symmetry break? And trying to generalize this so that we can involve more people in our field, such as mathematicians, who may not have the language of specific physics things, but they would have the language of symmetry and anti-symmetry and not symmetric. So can't forget about the electron beam. So just like the protons, people characterize the electrons with Gaussians as well, and kappas. So we have a core Maxwellian, and we have this kappa function for the halo part, and then we have the straw, the field aligned beam. Now in the solar wind, the straw is known to connect to the corona itself. And also it's known to depend on the location of the heliospheric current sheet. And so the heliospheric current sheet, for those who don't know, is this beautiful ripple of current that lies in a sheet and extends all the way out to the edge of the heliosphere. But what I was interested in, it's important to know that at 1 AU, for example, the HCS is stable and it's thick and there's not really much going on there. But when you get closer in, things are a little bit different. But first, I want to just mention magnetic connection, the process that converts magnetic energy to kinetic energy, and field lines reconnect, and the plasma jet flows outwards, and it represents a fundamental change in topology. So, moving to 16 solar radii, encounter 8, we saw this was a really interesting reconnection event that happened inside the HCS. First, we were really surprised that reconnection could even occur in the HCS, but as we're closer to the sun, it's actually just thinner and a lot more variable. And so here, this region right here represents the HCS. And so what happened was reconnection occurred inside of here. So these panels here are the span energy, like I showed before. This panel here is the beam electrons in pitch angle space. This is the magnetic field. So we can see is the beam actually leaked out of the current sheet from the reconnection. And so that was really cool to me. So finally got an answer for where the beam comes from. What was really curious, there are a lot of curious things about this, was, if you notice here, there's this onset of the proton beam at the same time that the electron straw goes away. And then the straw comes back and the beam disappears, so on. So it's a strange anti-coincidence between the beam and the straw. And even weirder, the field was mostly radial and quiet. Now, the electron straw, it only disappears by two things. One, a fundamental change in topology. Well, the field is quiet. Or two, scattering due to some mechanism. Not sure. This is actually an unsolved problem, but I do have some theories. So let's take a look at the VDF and really zoom in on what it means for the beam to leak out. So we have these 3 panels up here are the same VDFs I showed before. We're going to start, this is kind of like an animation that goes backwards in time because we want to follow these beams going outward. So you can notice that we're starting inside the HCS region, and the beam, there's not really much of a beam at first. Inside the current sheet, things are just a lot different than the ambient solar wind, and actually the VDF is more isocratic. So these top 2 panels here, the electron paths pitch angle distributions again, and here's the proton energy flux. So we're going to see what happens as we move backwards. So you can already see that 2 peaks began to form, and the length of this arrow, which is the magnetic field direction, is the Alfvén speed. The Alfvén speed is very, very low at this point, and separated by 2 Alfvén speeds, which is predicted by theory. And these separating even more so, and right when we get to that boundary, it leaks out. Very sudden. And you see, move a little bit further in time, we get that again we have this perpendicular diffusion of the proton beam. It goes away, comes back, goes away, it comes back again. And so, and also at the same time, there's this very powerful multi-scale wave activity also present, which is really exciting. So there's stuff at the, the kilohertz range. You can look at that at the AC power spectrum up here. And there's also, just as before, very strongly coherent ion scale wave power that is left-hand, for the most part, perpendicularly polarized in the spacecraft frame. The Doppler shift is very difficult for reasons I will not get into. But I was just really curious about this event because it just seems to me a wonderful example of how multiple scales could be talking to each other. And so I did some initial just regular bi-Maxwellian fitting to the protons and was able to compute a heat flux from that. And could see that this proton heat flux is coincident with all of these other things, coincident with the ion scale wave activity, the electron straw dropout, and the electrostatic wave activity even. And so, closer to the sun, we did expect stronger particle acceleration because there's more available energy. What we didn't expect was that we would have more energy scattering and leakage close to the HCS. And I'm wondering, could this be a significant energy driving region that we haven't really considered before? The proton heat flux, it could play a more significant role in energy transfer within the HCS and reconnection, and the proton beam could be providing a macro scale context of where we are, just like the electron straw. Got any questions so far?
How do you define a beam when you look at the distribution functions?
Oh, wow, that's a great question. So there's many different types of beams. So sometimes you can have a beam where there's a peak and then definitely another peak. And so that would be a sort of different type of beam. That would be definitely more unstable. But if there's not a second peak, if there's just a shoulder, I would still consider that a beam. But it just probably wouldn't participate as much.
Which one of the two peaks is a beam?
Oh, that's also a great question. So it's normally, I'll go back here. Normally, so I guess kind of see there is a peak right here. Here, there is a peak right here. And here.
Some of them look like, higher, the peaks that you would assume as a beam, they look bigger than the one that you would assume as a core.
Right. So yeah, I don't know if there is an answer to which one's a beam, which one's the core. I ask myself that question like once every 10 days.
These are really strong.
Yeah, no, these are very strong beams, and part of me thinks that maybe the fact that they are so strong and getting almost past the core, like it makes me feel like that it probably is not locally generated. It's probably maybe this beam is actually coming from the reconnection site over here. Or maybe, really we could be speak into a region where fast and slow wind is coming together. It's very possible. We're also, because of reconnection and the fact that if we cross the current sheet right here, this is actually a slow shock. And what's the role of a slow shock in all this? Slow shock creates a compression region, and so you can imagine a lot of energetics could be happening due to that as well. But yeah, which one's the beam, which one's the core? Flip a coin.
Are any of these the result of polyrhythms of energy?
What does that mean?
These different wave, maybe periodicity of the waves and the different combinations are causing these sort of structures to appear at different times.
Yeah, that's a good idea. Yes, exactly. Yeah, so yes, no, exactly, no. So I would love to show that, for example, these lower frequency waves, I would love to show that these lower frequency waves are sort of phase locked with some of these higher frequency waves, and possibly some really interesting wave interactions could be contributing to this dance. I mean, even I've even gone far as to I've been staring at these electron pads, and then I juxtapose these to when people see Kevin Helmholtz sensibilities at the heliosphere. It's actually almost the same signature. And so what if what if this is actually a surface wave? What like, what if the energy transfer is actually coming from that much larger scale, a vortex by the current sheet and then just cascading. Yeah.
I'm just hearing music.
I see music everywhere.
I can't wait.
Oh, yeah, okay, cool. So,
Wow.
so that, I see music everywhere and, I was looking at these waves and I was like, oh man, like, I wonder if I can hear any of this stuff. Yeah, at first, these are in the kilohertz range, so it's actually already in the audible frequency, so I don't have to do anything to the data to just turn it into sound. If anybody wants to know how to do this, I made a Jupyter notebook and I'm happy to share it. And I have a Jupyter notebook about other things too, if anyone's interested. But I was looking at these waves and I was kind of hearing this stuff. It kind of, it's very broadband, so it kind of sounded a little bit like noise. This stuff was kind of too low in amplitude for me to hear, but then I was like, oh man, this wave is kind of coherent, but not very high amplitude. And then I was looking at the current sheet crossing, which is a whole mess, whole nother talk about this. But I did notice, okay, just about a little bit further into the current sheet, there's this nice wave here. And let's see what it sounds like. I don't know how loud this is. I think that this is direct.
Is there an indicator that I'm not seeing or something?
Oh, yeah, no, I should have put that on, but I don't, but just use your imagination.
Were we going across the whole thing in that amount of time?
No, we're not.
There's somewhere in there.
There's someone.
Yeah.
Yeah,
Awesome.
So this is kind of converting into the data from the AC power, that second panel into audible range over here.
Oh, no, I didn't even have to.
Just,
It's already in the audible range.
oh,
So our ears can
that-
hear.
so that's direct. I'm trying to understand what the instrument does, how it gets, it's not like taking some other data into like the frequency domain, it's not, it's like direct.
Oh, yeah, so at first I looked at the spectrum. So to see where the coherent waves would be. And then once I said, oh, okay, I want that time slice, then I actually downloaded the actual waveform. And then just converted that to a wave file. It was surprisingly straightforward once I figured it out. And so, yeah, you can get nuts with this.
And this is data that the spacecraft is recording as it's flying at how fast?
Very fast.
Okay.
Yeah.
Yeah, that's interesting.
Yeah. But yeah, so this is direct evidence that there is space whales. Look out for the nature people.
Space whale.
I think it's the Verniero. I think it's actually it's electrostatic whale. But all this to say, the heliospheric current sheet is a highly dynamic and beautiful object that I think needs to be revisited, because at first we pictured it as just this 1D or maybe 2D thick sheet of current that really didn't do much except for separate negative and positive polarity. But we really need to think about a 3D picture of this, because really to understand the interval I was showing, there's got to be some sort of three-dimensional reconnection going on to explain all of those dynamics. And I know that the Magneto tail emits these surface waves and it flaps, and so what if we're witnessing the flapping of the HCS just like the Magneto tail? I see no reason why not. Is the Helio tail also flapping? I don't know. But so Parker Solar Probe is really showing us all of these wonderful opportunities to assess these fundamental processes. So now I want to read a poem that I found on my computer from my past self a couple of years ago. I just thought it was neat. called entropy. Love is chaos. Chaos is love, an irreversible process that is poorly understood. A mystery that humans have declared unsolvable. A system that is greater than ourselves. I am the coffee and you are the cream. We begin to mix, but as we mix, we do not know our fate. We couldn't possibly know that to be unmixed is that of a fallacy, farce, an impossible task. For in love to love and to be loved, the entanglement is too complex to be undone. I cannot unlove you. The coffee cannot unmix from the cream. So now let's move on to some higher level mathematics. So I love to generalize. Magnetic reconnection and instabilities are both mechanisms for sudden explosive energy release. And this onset of energy release is analogous to non-integrable solutions of a dynamical system. And these words, integrable, solvable, invariant, and symmetric are all equivalent to me. And so my question is, can the study of energy storage and release in heliophysics be generalized to classifying symmetries and asymmetries of the system? Because if it can, then I can call all my math friends and we can solve everyone's problems. Almost everyone. But where does the energy go is analogous to where does the symmetry break? So a little bit about dynamical systems theory, in case no one's heard of it. There's this beautiful area of applied math. In plasma physics, you use it already. The set of particle orbits and phase space forms called a topological manifold. So the word manifold is just a fancy word for a very smooth surface with really nice properties that are convenient. It's able to predict sources and sinks, kind of like predator-prey models, and also instabilities. It can identify invariant and stable configurations in space, and can characterize ergodicity and entropy and all that fun stuff. And could also explain formation of coherent structures and how energy is trapped or dissipated. There's also one of my favorite topics of applied math, which is knot theory. William Thomson, aka Lord Kelvin, way back in the day, when people still thought they were ether, Lord Kelvin had this theory of vortex atoms. So this picture of the atoms were just weaving through the ether in a knotted structure, and that each atom would have a different knot. So a knot is really literally, tying your shoes. But how to distinguish different knots is just by the number of times that crosses over each other. And so I guess the idea was that every element would have a unique knotted structure. These ideas, even though the ether was disproven, unfortunately, this idea about the atoms was also died away. But I do feel like this concept of the vortex atom, it could be still relevant. Knot theory has been very popular in the last 10 years because of machine learning and a lot of other things. Knot theory is used in fusion to try to store energy. It's used in molecular biology because of DNA is a helix. So think of it as a knot, and people actually use knot theory to try to classify protein structures now. Knot theory is also used in quantum physics, studying entanglement. And recently it's gotten its way into electromagnetism, and specifically wanted to highlight in 2013, Candelaresi was able to show with the resistive MHD simulation that if you start with a knotted configuration versus an unknotted configuration of helicity, so helicity is just a measure of how field lines are twisted, the knotted structure took a lot longer to decay its helicity than the unknotted structure. So knots could be a really useful way to try to understand how energy is stored.
Over 5 minutes.
Okay, great. And then there's also this really fun shape called a hot vibration, which is another knotted structure. And basically every great circle maps to a different maps to a different link, and it creates this. We go to one dimension, we go to a hypersphere and then map it back down and create this nested torus. I just saw in the hallway at the physics building, somebody was using this shape in solid state physics. So that was cool. So I really hope that that space physics, borrows some of these ideas as well. Kind of skip over this, but knots theory is really awesome. If someone wants to talk to me about knots, please give me afterwards. So I just wanted to say, if you take your data and you actually plot it instead, not versus time, but do a 3D photogram, this example right here, I got a sphere. That's because these were all Venic fluctuations. These are called the switchbacks. And it had this nice simple shape from a seemingly complicated time series. Juxtapose that with a seemingly simple time series, and you actually get a knot. So what does that mean? Tangled information? Maybe. But I'll just close with this. And I'll take questions. Where does sun break symmetry, all these things. Don't want to go over my time, but thank you so much.
Are there any questions in person?
Oh, earlier, well, with the data driven, different bases to, and then there was a plot showing the entropy. Can you help me through, all the steps going from that data driven metric?
Oh, yeah.
Interest, like entropy, the basis
Yeah.
to, computing entropy?
Oh, yes. So where is this? Can I use the board? Yeah, so basically, can I use the board?
Yeah.
So the matrix counts, and it depends on time, energy, and two angles. And then you can decompose that as a sum of these weights. So we have weights as a function of S and T, and then and other coefficients that are going to depend on energy and angle. That's what you get from the singular value decomposition. You get these weight functions, and so really the entropy was just computed as just n log n times the weight on the time. Cool.
Thank you. Yeah, another question here regarding your point about the source of the beam. Where does it come from? I don't quite see the puzzle with the electron straw yet, but I was wondering, is there a sense that you said there's maybe a shock wave, even there's a shock at that boundary? Is it possible some of the ions are reflecting off the shock the same way they reflect off the bound shock? And that some of that's happening, or it could be reconnection driven.
Oh yeah, I've definitely thought about that possibility.
Okay, but I don't know why the straw would somehow be anti-correlated with that, but nothing the
Yeah.
straw would be reflecting. So
Yeah,
sure.
I would love to discuss that possibility later, because that would be awesome to show that.
Yeah.
Because I think that we're getting into regions that look a lot like the bow shock. These distributions look a lot like what happens in the foreshock region.
Any other questions? So we don't have any questions online. It seems like if you don't hesitate to have some time. Oh, you go ahead if you.
Oh, no, I was gonna ask, I was gonna stop by after, the Jupyter, like the tools that you developed, are they on GitHub?
Oh, yeah, I can, yeah, should I put it in the chat? Or-
You can.
Cool, yeah, and I could also send you, or, I could also send you, I have a description of everyone too, I can maybe just email to you first. But,
Thank you.
cool, yeah, I have a tutorial on how to actually analyze the Parker Solar Probe data.
Oh,
For how to plot these VDFs, and also, I'm continuously adding to it.
You wanna chat about what we're maybe doing tomorrow?
Oh, yeah, wait, so does everyone know who you are?
I don't think so.
Oh, you want to introduce yourself?
Yeah, I'm Marty Quinn. I used to work at the Space Science Center, a couple of the IBEX team and the crater team. And I am a specialist in data sonification and data visualization, but sonification is my love, turning data but into music. So we're using the full spectrum of musical instruments, percussion, rhythm, concepts of coming and going, the presence of the sound or not presence of the sound. And it's very effective. I've worked on many projects in like 30 years doing this work. I've developed software to translate the data into these musical structures. And in the process, I learn about the data, but actually the principal investigators learn about the data in new ways. We've discovered new winds at Hubbard Brook experimental forests because of the data visualizations and the music. We've discovered errors in the data from the music. And then we're looking at the similarities between this data and a project called Rock Around the Bow Shock, which we did at UNH from the what project was with the Bow Shock, the 4 instruments.
Cluster.
Yeah, cluster, from the cluster and spacecraft. And it used 39 instruments to represent these the spectrum bands as chords of music played by 3 distorted guitars. But the actual notes, like you represent that whole spectrum with like 16 notes on a guitar. And then the volume of those notes is the brightness of the color. And so you literally can hear it changing as you go through the bow shock. And so
It's so similar to the bow shock, so I wonder what it's gonna sound like.
yeah, and so using music, it's almost like a 3-dimensional presentation to the brain. Because we can use the full spectrum of timbre, like an orchestra, and then we can, I've gotten up to using 1,000 voices at a time to hear 1 million pixels in 40 seconds from an image. It's fascinating to hear. We've done work here at UNH on the IBEX, this ACE spacecraft. I've worked on Marsch sonification and climate data from the Odyssey program. And so I had my eye on solar probe data for a long time, 8 years or whatever. I tried to do an educational outreach thing for one of the other solar probe thing, but it didn't get whatever, funded or whatever at the time. So I'm looking forward to maybe doing something like this and seeing what it sounds like, because you've got such beautiful data there. It's so interesting.
Yeah, and I just want to, I get so tired of looking at a computer screen. I don't wanna, put on my headphones and go for a walk, and I still get work done.
Exactly. And maybe learn something.
Oh, yeah, probably.
Well, thank you very much for. See you next week, everyone. We have a presentation from someone in the NASA division, Space Science Fiction. So, bye, everyone.